Thank. Okay. So, hi everyone, and this is a presentation about attention mechanism, transformers, BERT, and GPT at Professor Crowley's lab in UWaterloo. So, attention mechanism. First up, when we look at some scene or some image, for example, when we look at Mona Lisa portrait, okay, do we care whether there's a river behind her, or what do we focus in the image in our visual system? When our eyes will focus on her face, her lips, her smile. Yes, this is how we focus. So we focus on some parts of the visual scene, not all the parts. In digital imaging, we focus on some pixels rather than all pixels. So also when we are reading some text, when we do fast reading, one of the techniques for fast reading is skimming, and also only attending to important words, right? We don't care about all of the words, only important words. This makes the pacing of reading very fast. So, and as you see in both reading fast and also looking at things, we are waiting. We are waiting things. We are waiting pixels. We are waiting words. Some words are more important. We wait them more. Some words or some pixels are less important. We wait them less. So this is just waiting. And this notion of waiting is used in machine learning named attention, because we are attending to things differently. Okay.
So one of the questions again is almost the context. When we're looking at a painting, we're seeing this. Do we think about, because we just say that and we'll say, oh, you're looking at a painting and paying attention to this. But what's the task that you're doing when you're looking at a painting, right? Because in machine learning, we have to say, why are you waiting? You're waiting this because you're trying to classify or identify the person, do object detection or something, right? When you're looking at it, is that notion of what you're doing by looking at it, what task it is, would that change your attention? Right? If I told you to tell me who the artist is that drew this, or to tell me what year it was in, or just told you to look at it, would you attend to different things? I guess that's my question.
Yes.
Is that relevant?
So yeah, the question is whether our attention differs if we know if the task is different. For example, if maybe someone tells us in the portrait what colors are used, then our attention will be different. They will see some green color is in the background and these things. Or someone might say, what is the subject of this portrait? Then we will attend on it to the face. Someone might say, what is the clothes of the Mona Lisa in the portrait? Then we'll look at attend to the clothes. Yes, of course, it depends on the task. It depends on the task, but in all of the tasks, we attend to something. We attend to something. We don't attend to everything equally. Even if we attend to everything equally, we are still attending, but with equal weights, right? Okay. So in the sentence, for example, Mona Lisa is a portrait painted by Leonardo da Vinci. Mona Lisa and portrait and Leonardo da Vinci are important. Is painted by, these are not important. Okay, so, and also about autoencoder and context vector. So assume, so when we have an autoencoder, it has encoder and decoder, and there is some latent space in the middle, right? And you can assume that encoder gets something, encodes it to some code layer, or latent layer, and then decoder gets that and outputs that. We can have different types of autoencoders. One of them is reconstruction autoencoder, where the output of autoencoder should reconstruct the input. That's one thing. However, assume that I get something and I try to transform it. For example, I get an elephant as the input of encoder, a cartoon elephant, and then I output a real elephant. In the middle, in the latent space, in the code space, I have the concept of elephant. Whenever I talk to you about elephant, you imagine the elephant in your head, in your mind. Then I think it's related to philosophy of mind. You have the concept of elephant in your mind. Do you have the elephant in your mind? Of course, but you have the concept. Does it matter whether the elephant is thin or very heavy? No, it doesn't matter. All elephants are in that concept, all types of elephants. So only the concept is important, and the concept is in the code layer now. So that's we can see, and as you see, we can use it for different things such as domain transformation, adaptation, domain generalization, because we can change the domain by the through the concept, and that concept can be modeled using a context vector. So a context vector you can denote it by C. It is a p-dimensional. Assume that the hidden space or the latent space in the autoencoder is p-dimensional. Therefore, it will be p-dimensional context vector C. Then we can have a sequence to sequence model. What is a sequence to sequence model? Assume have an autoencoder which gets a sentence in English and outputs a sentence in French or something else. So again, we have the concept of that sentence in the middle, and we have a sequence as input, we have a sequence as output. Therefore, you can call it a sequence to sequence model. Okay. A regular sequence to sequence model is like this in this figure. So we have xi minus 1, xi plus 1. It's a sequence, right? Then each of them can generate some hidden vector denoted by h. Okay, this is what is done in RNN and LSTM, recurrent neural network and long short-term memory networks. And we also have W matrices, just learnable parameters of that network. Okay, the weights. And in the middle, we have a context vector. So this is in the latent space between encoder and decoder. And then we have also the W matrices, and assume the hidden vectors corresponding to the hidden vectors in the encoder are called L, denoted by L in the decoder. Okay, so I have L minus 1, Li plus 1, and etc. And each of these, they will generate Y, which are the outputs, Yi minus 1 or Yi plus 1, something like that. So an example, for example, X are these X's are the words in English, and Y's are the words in French, something like that. As you see, we have the probability of Yi given. So every word given the previous words, you can see it as a function of the previous word, the Li, which is the hidden vectors in the decoder, and also the context vector. And as you see, the context vector is kind of having the information of all of the hidden vectors in the encoder. Why? Because it's exactly equal to the in this model, it's exactly equal to the last hidden vector in the encoder. So see, the last one will be exactly C. The last hidden encoder is C. And as they are coming back to back, HI has the information of HI minus 1 in it, HI plus 1 has the information of HI in it, therefore C has the information of all of them. So this is what RNN and LSTM are doing in sequence to sequence model. Then we can, I think I already
know that they're summarizing to that context.
Which
vector,
yes,
is essentially summarizing and encapsulating the encodings for the previous words up to that point.
Exactly. It's encapsulating the information of the input sequence. For example, when I say this is an elephant, then this context vector is the concept of being an elephant. So,
but is it all previous words forever, or is some limit that way?
Oh yes, there is some window. Although RNN tried to do it for infinite recurrence. However, they found out that they can't do it. There is a memory limits and these things. Therefore, they said, okay, we need to have long short-term memory networks. And what do they do? An example of LSTM. Well, why do we need LSTM? I give you two sentences and you will understand, I think. One example is the police is chasing the thief. Okay, police and thief are related and they're very close to each other. So we need short-term memory for this. Another example is that I was born in France. We had a great life there with my family. We traveled all over the world. I remember I had a great time with my father. That's why I can speak French. French is at the end. France was at the start of the whole paragraph. A human's mind understands that they are related. So machine should also understand. Therefore, we need long-term memory for that. So for modeling these two things, we need LSTM. Therefore, LSTM came up. And we see that here, that attention mechanism came and just outperformed LSTM and RNN. Nowadays, they are not used anymore in NLP mostly. So yeah, and as I said, we have only one context vector C, which is the last hidden vector in the encoder. This is used in RNN and LSTM. Now, let's use attention in a sequence-to-sequence model. If we do that, then what happens? In the sequence-to-sequence model with attention, the probability is like this. So the probability of every word, output word, even the previous words, output words, okay? What is it? It's a function of, again, yi minus 1, the previous word, li, the latent or hidden vectors in the decoder for the i's. So see, this is yi, generated from li. Therefore, yi is related to li, also to the previous word, yi minus 1. Ci, the difference of equation 2 and equation 1 is Ci. So here we have Ci. Without attention, you only had C here. Why? Okay, without attention, we only have one context vector. We have only one context vector, which is one concept. However, with attention, we have several. We have several context vectors, and it's not anymore equal to the last hidden vector in the encoder. It's kind of a linear combination of all of the hidden vectors in the encoder. So we have several of them, right? H minus 1, Hi minus 1, Hi plus 1, a lot of things, Hi's in the encoder. Now let's have a linear combination, weighted sum of them, as shown in equation 3. So Ci, we have several Ci's, and we can play around with Aij's in order to have different Ci's, okay? So Aij is the weight of Hj for the ith context vector, okay? That's the thing. Yes, yeah, you can see that, yes. So now, this weighted sum, why do we have this weighted sum? For a specific word in the sequence determines which words in the sequence have more effect on that word. And we'll see some examples. For example, the police is chasing thief. Police has more effect on thief. Is has less impact or relation with thief. Is the police is important. So there is difference how much thief is attending to the words behind it, something like that. So we can see CIs, we have different CIs because we have different attentions. We don't want to have the same attention. So in other words, it determines which words of this specific word attends to more. And this is attention mechanism. Okay. So here we can define Sij as a similarity, S standing for similarity, of Li minus 1 and Hj. Hj, doesn't matter, Hi or Hj. So what does it mean? What does it mean? Hj is related to Xj, right? Li minus 1 is also related to Yi minus 1. Therefore, what?
Why is it I minus?
Because Yi minus 1 is generated from Li minus 1. What do you mean?
Why is it similarly of Li minus 1 and Hj? Why is it not J minus 1?
Give me a second to think about it.
That sounds familiar.
Yeah.
Right.
I think this is the reason. I think as far as I remember, no, you're right.
Well, your figures on the computer. Yes.
Okay, but and the thing, you're right, but I need to think about it. But Anyway, what I want to say by this equation is this, that yi minus 1 or yi, which maybe yi is correct, li might be correct, doesn't matter. Yr or yi minus 1 is related to li minus 1. Assume it's related to yi minus 1. hj is related to xj. When we take similarity of li minus 1 and hj, it's like we are taking similarity of yi minus 1 and xj. So it means that what word in this French sentence is attending more to which word in the English sentence? See?
Right, the similarity of the context vectors for that associated with each word. For the decoding of that word.
So yeah, the decoded word is French, for example. The encoded word is in English. Assume I don't know the words in French. I think student is still student. What? Student. Okay. When we say, for example, we say I'm a student, then there you say la studa, for example. That studa is attending more to student in English, right? Something like that. So you see how the output words are more related or attending to the input words. So that's the thing. And yeah, how much impact of the input xj on the output yi. Score Sij shows the impact of the jth word to generate the ith word. Right? Okay. And we can learn this similarity notion by backpropagation. We will see. Okay. So to make this score a probability, this score is not necessarily a probability, right? So we have several techniques in machine learning to make things probability. If we have a scalar, one scalar, it's not between necessarily 0 and 1. We want to make it behave like a probability. One technique is logistic function or sigmoid function. However, when we have a bunch of scalars, we want them to behave like a discrete probability distribution. Then what do? One technique is that we divide each of them by the sum of them. Then they will sum to 1, and they will be between 0 and 1. Another technique is using this. It's softmax form. So rather than saying in technique 2, which I mentioned, was this, but compare these two. This is softmax. And what does it do? What's the advantage of softmax? This is Gaussian distribution, so it makes them Gaussian. And why do we have this? Just for the sake of normalization, to sum to 1. Okay, so these are the 3 techniques that I mentioned for making something behave like a probability. And now Aij, we know it is behaving like a probability, and it has Gaussian distribution. So this is similarity in a probability way. Therefore, we have a score vector behaves like a discrete probability distribution. Therefore, equation 3, which we had this, I'm repeating it here. Cij, do you remember Ci was a linear combination? Was a linear combination of the latent vectors. The weights sum to 1. Now Aij's is the weights sum to 1, and the weights with higher values attend more to the corresponding hidden vectors, right? Okay. Now we also, let's see an example here where the FBI is chasing a criminal on the run. So the more we go in this word by word in the sentence, we'll see some words. Every word that we are focusing on is attending more to some of the words before that, and attending less to some other words. For example, the FBI, starting with the, doesn't matter. FBI, there is not that much important. Is attending more to FBI because FBI is chasing, right? When we go to chasing, is not much important, but FBI is a bit important. So the intensity here shows how much it is attending. Maybe chasing, criminal, and then so on. So for example, run here is attending to criminal because criminal is on the run. Also chasing because someone needs to run, so the other one chases that. So that's the thing. Okay, and as you see, we don't only want to have embedding for every word regardless of the context. Context is important. Therefore, we need to have a composite embedding in order to embed the words all together. And we care about the embedding of the word in the sentence. Okay, this is a bit, let me open a parenthesis here, a short parenthesis. This is a bit related to analytical philosophy. Are you aware of analytical philosophy? So we have two types of philosophies. One of them is continental philosophy. The other one is analytical philosophy. And analytical philosophy, which started about the start of the previous century by Russell, Moore, Frege, and Wittgenstein. What did they say? They said the philosophy of language. Language is very important. What we do is by our thinking is because of our language. If you take away the language, we can't think. We can't do anything. Before that, philosophers thought that we think, and using the language, we can just transform it. However, no. Philosophers found out that we think by the language. So that was the fundamentals of the analytical philosophy. And in analytical philosophies, I think it was Frege who mentioned that there is a principle of context in the sentences that we read. So the context is important. Also, Wittgenstein in his philosophy later, because we have two types of Wittgenstein philosophy. Early Wittgenstein and later Wittgenstein. He changed his philosophy in his life. Later, Wittgenstein said that the context is important. Where we use the word is important. Where we use our language is important. And that's why he created the concept of linguistic game. You can take a look at that. It's in philosophy, linguistic game. So we play some games. When I'm talking to you guys right now, I'm talking in an academic way. When I go to a car dealer, I talk in another way. So these, because the words that we choose is based on where we are using them and the context. So this is how it is. And as you see, it's related to here. So related to the context that we are doing things or having the sequence, we need to embed them differently. And now you see the lack of word-to-vec and glove. Are you aware of these? These are some methods in NLP, old-fashioned NLP, which said that let's embed the words just individually, and I don't care. I don't care about where they are used. So I have an embedding for every word. However, because of this, you see that there is a lack in them. For example, I give you an example and you will understand this lack completely. Consider the word bank. Okay, bank. Word-to-vec or glove give one embedding for this bank. However, I use it in two sentences. Money is in the bank. The second sentence, in the bank of the rivers, we have a lot of vegetation. So as you see, we have two different, completely different meanings for the word bank, but they have the same embeddings in word-to-vec. So this is the problem with word-to-vec and glove. Therefore, some things such as attention mechanism came in order to take care of the context. Okay. Now query retrieval modeling. So consider, who here knows about the database and query retrieval and these things? Okay, so in database, if you have passed the course on that, so you have a query, you have a database, so we have some keys and values, and based on the query, you will get some value. For example, also dictionaries are related to this, and hash tables and these things. Okay, so database with keys and values. Okay, now this is a hard definition of a query retrieval. Okay, we have a query, it matches with one of the keys, it outputs one of the values, right? However, let's have a soft definition of database. Let's say that let's compute the similarity of query with each of the keys. The similarity with each of the keys, it gives us some weights. Using the linear combination of the same weights on the values, we get the value, output value. So this gives us, for example, A1, A2, A3, and these things, and then we use the same weights here, and then the same weights on times the values will give us the output value. So as you see, we have a soft definition of query retrieval. So similarity of the query with all of the keys rather than one of the keys. And here we can define the concept of attention, which gets the Q query, the keys, n and n values, and outputs these. As you see, these are weighted sum of a linear combination of the values. Okay. And SI, let it be similarity between the query and the ith key. Okay, so we have n SIs, S1 to Sn, right? And again, AI in a softmax form. Why? Because we want it to behave like a probability. Okay. Now, an illustration of what I said. So we have, for example, here we have 4 keys. We have one query. We calculate the similarity of query with each of the keys. We'll have 4 similarities, S1 to S4. We use softmax to make them like behave like a probability. And for softmax, we use all of them. We need all of them in the denominator, right? And then we add A1 to V1 A1 times V1 plus A2 times V2 plus A3 times V3. So we'll have a linear combination of the values, and this gives us the attention. So clear?
How did we lose
What?
Because in equation 3 we had the C
Equation?
we had AIJ before. So we had
3?
AI before. Yeah, if we go back to equation 3.
Oh, yes. Okay.
Okay. So we had the CI and the AIJ and HJ.
Yes.
Now we just got AI. So we're summing a little earlier somewhere. Like probability, or maybe V is not H, that's why, but we changed from H on these.
Yeah, so here, there in the query retrieval that I mentioned, we have one query, but here we have several. Well, give me a second. Yes, we have CIs here, but there we have one query. But I'm building up the concepts. So
It's a different model.
yeah.
They works directly,
Yes.
but now they got more intermediaries, right?
Yeah. So I'm gradually building up to define the attention mechanism.
Well, I know. Yeah.
Yeah.
I always find this part because it's like the key value parameters. Like why this? Like this thing now, everyone assumes is where you start. Like attention is key. I've literally heard people say, "Oh, attention is key value pairs and queries." That's what it is.
Yeah.
And like in my course, we start with like, well, attention was for explainability in images.
Yeah.
You know, and that's what people were using it for. There were a couple different things about attention when we were talking about. But why is about this key value query? Are these essential core things? Like what's
the reason is that, for example, you can see the keys as the pixels. So we have a weight of keys or values or corresponding value. So keys or values as a pixel. So with a weighted sum of we are weighting the pixels. So when I'm looking at you, for example, I'm weighting the pixels around you more than here.
So the value is the weight, or the value is a label or something?
So I'm saying that, so did you get the idea of weighting? Now we can use the idea of weighting in database query retrieval. Okay.
Yeah.
So that was one thing, weighting and attending to the pixels or the words was one thing. Now I'm building up. I'm using that concept for the sake of query retrieval in databases. And this concept of soft query retrieval in databases using the weighting is used in transformers. Okay. So the similarity SI can be any notion of similarity. Some examples are inner product. Inner product is an example of similarity. Yes, shows how two vectors are similar. Query transpose key. Okay. You can also have a scaled inner product. So you have query transpose key over the square root of P, where P is the dimensionality of Q and K. Also general inner product, you can have W in the middle. Okay, you can have W in the middle as some learnable parameter to be learned by backpropagation. Okay, so you can have also WQ transpose Q and WK transpose K. So WQ and WK also are learnable parameters. right? So these are additive similarity.
These are more nice, like mentioned all here's called a number.
Yeah, yes, they are scalars and they output the similarity. I think for these three, you will understand why they are similar. So because it's an inner product. Why is the equation 12 similarity? Because if, for example, in 1D, assume in 1D, if Q is going to the right, K is also going to the right, they're added. If Q is going to the right, K is going to the left, they're subtracting with each other. So they are not similar.
But really the central thing is that these are all ways of taking two vectors with information, I guess vectors of the same length, right?
Yes, they are. Q.
Yes, is a table. You get one element of that. Then when you get Q and Ki, you get two vectors that have information about the same features or same things or entries, right? Bunch of numbers. You're combining these vectors with some unique weighting that is per element and getting a number.
Yeah. For example, the police is chasing the thief. You can see Q as the thief and K as the words before that. The police is chasing. Okay. And then you will see that which one is more important. You'll see the similarity of thief and police, for example, or the relation of them is high, right? Something like that. So it's showing how similar two words or two tokens in the sequence are.
The whole vectors.
They are vectors. They are vectors.
Human Ki vectors.
The vectors, and we will see. You use, for example, word2vec, word2vec embedding vectors of the words.
Every word uniquely.
Every word is a vector in the word2vec embedding space, and then we use those words in those vectors in order to calculate the similarity. Yes.
And turning them into a number.
Yes.
Based on all of the words.
Yeah. There's a similarity. Okay. Now, so we have attention. It calculates attention, target word or query with respect to every other word or keys, which comes back and forth. Sometimes only back, and sometimes back and forth. We'll see when each of these are used and how similar the other words of the sequence are that word. How impactful, how similar they are. For example, I am a student. We're processing the word student. The other words are I, am, and a. Then if you take similarity of I and student, for example, is 0.7, am and a student is 0.2, a and a student is 0.1. They sum to 1. So they are at probability. Therefore, the attention value for the word student is 0.7 times V I, 0.2 times V am, 0.1 times V a. Okay. Assume an example. Yeah.
That's the one that current ones that they've learned about.
Yeah. The similarity are learned by backpropagation.
So you already have some basis.
Yeah.
How it's combined, and obviously.
Yeah.
Does it come from the word in there? I guess that's a problem thing with. Really, there were some things before we should talk about using the phonemes and the letters and encodings, but from experience.
So here, again, we take the d-dimensional representation of words taken maybe from some word embedding NLP method. Examples are word2vec globe. So as you see, transformers are using word2vec and globe as kind of input. Okay. So query key value are projection of words onto p-dimensional, and r-dimensional subspaces. So consider xi. So these are the word2vec embeddings of the word ith word in the sequence. Then we have some learnable parameters, wk transpose, wq transpose, wk transpose, and wv transpose. It gives us some some vectors qi, ki, and vi. We assume that qi and ki should be the same dimensional because we need to have inner product between them, and value can be different in terms of dimensionality. Okay, so and here we can stack them to become matrices. So we can stack them column wise to become matrices x, q, k, and v. X data, input words, q query, k key, v values. Okay. Then, as you see, these are inner products. Therefore, you can see them as kernels. So you are, for example, when you say Q transpose K, similarity is like behaving like a kernel matrix. Okay. And now compare. So, by the way, equations 7 and 8. Let me bring them. These two. SI similarity of Q and KI, and AI is e to the SI, and all of these things. So if I want to write them in the vector format or matrix format. So we'll have these. So let me write them down here. Similarity Q and KI. AI is e to the SI summation of e to the SK. So again, going back to where we were. So here, so we have, as you see, similarity, we said that it's like an inner product, Q transpose K, right? Also, this is a scaled, I'm using a scaled inner product, right? And softmax is because of what we had. This is softmax form, right? Okay. Yeah, this is similarity, but behaving like probability because of some. Yeah, and V, why do we have V? So these are the weights, AI, V. So we have weighted summation of values, exactly what we have in soft database query retrieval. And if the queries, that keys and values are all from the same words in the sequence, then it is called self-attention, because we are calculating the attention of the words of a sentence with the same words in that sentence. So we have self-attention. Okay. If we calculate the attention of words in one sentence with respect to another sentence, then that's cross-attention. Okay. So we can have attention in other fields such as vision and speech. For example, we can have blocks of image. And these blocks of image, we can see which block of image is attending to which other block of image. And as if we consider the attention of blocks of one image with respect to the same image, then that's self-attention, right? We can also have cross-attention between two images, right? And we can use that, for example, if encoder is CNN on the image, applying on the image, decoder is applying on the words, then we can use it, for example, for caption generation, these things, right? Encoder encodes the image into some concept, and decoder gets that concept and outputs the caption text for it.
So the first area I heard of attention.
Yeah, okay. Yeah.
The news.
Yes, exactly. And attention in other fields, usually many papers which are using attention at least several years ago, they were titled in this way: attend, tell, and do something. Some examples are show, attend, and tell for caption generation. Caption generation for images with ownership protection. Protect, show, attend, and tell. Text reading from images containing a text. Show, attend, and read. These are the titles of the papers. Translation of one image to another related image. Show, attend, and translate. Visual question answering. Show, ask, attend, and answer. Human-robot social interaction. Show, attend, and interact. Speech recognition. Listen, attend, and spell. Okay. And all of these can be modeled as sequences. Now transform. Okay. As was explained before, an autoencoder takes some input data, encodes it into some concept, and then decodes that, transforms the input to a related output. Hence the name transformer. Okay, it transforms some input to some output. Yes, you can. Yes. Okay, an example of transformation is translating. Another one is image captioning, translating an image to a caption or something. So transformer, therefore, is an autoencoder. It has encoder and decoder. Okay. An autoencoder named transformer. It has encoder. It has encoder.
It is an encoder dash.
So it's an autoencoder. You can, but I understand what you have in your mind is saying that autoencoder is only reconstruction autoencoder. I believe no. I believe.
That's what everyone thinks.
Yeah. Yeah.
I've heard everything, but autoencoder usually think it's a narrow one, reconstruct, the label is data. That's what
Yeah.
people think about.
That's reconstruction autoencoder.
I see.
Yeah, we have different types of autoencoder. We have variational autoencoder. We have autoencoders for generative models like variational, adversarial autoencoders. We have reconstruction autoencoders, as you said. So one autoencoder is transformer. So it transforms something to another thing. It was proposed in the literature for the sake of transformation. Okay. This is an autoencoder. Sorry for the quality of the image, but that's fine. So the structure of transformer is depicted this, an autoencoder. It is an autoencoder having encoder and decoder. So this is encoder, this part, the left-hand side. The right-hand side is decoder. Okay. Here we have inputs. Here is the concept or context vector, latent vector, the latent space. Here we have outputs. Outputs again here are fed as the input of these two. So its decoder is getting both concept, latent space, and the output of decoder again. Okay. Now let's go into the details of encoder and decoder. Encoder of transformer. So this is encoder zoomed in. Okay, let's see. So encoder gets the encoder part embeds the input sequence of vectors x d by n. So I have d-dimensional vectors, assume word to vec, and n of them, n words. I'm stacking them column-wise. And it encodes them into context vectors with attention mechanism. Okay, in the latent space. So and it doesn't have. We will see that. With transformers, they don't have any recurrence anymore. That's why they outperformed RNN. They said attention is all we need. We don't care about recurrence anymore. Yes, attention is all we need. We'll see that. Okay, so therefore, as we don't have any notion of recurrence, we don't have any notion of order. Order is important in sequence. So we have two types of data. There's some usually regular data sets that we don't care about order. If we care about order, that's a mistake in those data sets. In some data sets where it is sequence-based data set, we actually should care about order. If we don't care about order, that's also another mistake. So here we should care about the order of, but how? How? They said an idea, a trick. Let's have positional encoding, and which we'll see. Let's add a vector to the data. So here we are adding some vector to the input data, okay, to the input embedding, which encapsulates the information of position in the sequence, okay? And let's see how we can find that vector, calculate that vector encapsulating the information of order or position. They came up with this. Interesting. So consider the position vector pi to be a d-dimensional vector, okay? Data is also d-dimensional. So the position for the even elements in the vector, let's use sine of I over this formula. For the odd ones, let's use cosine. Okay. What is I? I is kind of the order. Which word in the sequence? I. And what is J? J is actually the dimensionality in the position vector, related to the dimensionality of the two. So this is evens, this is odd.
What determines the dimension?
I consider it to be d-dimensional. Then I fill out this vector in this way. No, D is the dimensionality of word-to-vec embeddings, which is the dimensionality of data. Input data. No. For example, 200 and something, to the dimensionality
Oh, I
of
see.
word-to-vec embedding. Yeah. So here, as I said, we've used this in order to fill out the position vector, and here is a visualization of this vector. So this axis is the token position. So position I is 1, I is 2, position. The y-axis. The x-axis is the dimensionality of P. So each of these is a P. So this is P1, this is P2, this is P3, etc. Okay. So this is a P vector. Each row is a P vector. No. P I calculated by equation 17.
In position I.
So yes, for the even dimensionality of PIs, I use sine. For the odd ones, I use cosine. I mean this. For this is odd, this is odd, this is even.
Yeah, that's why
this is odd, this is even. Right? But they are different. Why? Because they have I in them. They have I in them. They have J in them too. I is the position in the sequence, xi, I. The first sentence, second sentence, yes. I is the position of the xi in the sequence. J is related to the dimensionality of P. 2J or 2J plus 1. Let J be 0. We should use this. J should be 1. We should. Didn't you understand? Okay.
You said 7 things.
So consider x3 is the third word in the sequence. So I is 3. Then I have P3. I have P3 1. I have P3 2 until P3 D. This is a vector, D-dimensional vector P. For calculation of P1, I use this odd. I put I3 and J. What is J here? What is J here? 2J plus 1 should be 1. J is 0. What is J here? 2J is 2. J is 1. Then 2J plus 1 is 3. J is 2. Isn't it obvious?
Why are we doing this? You're creating another encoding that represents the position of that.
No, I'm using these, the inputs of the.
Yeah, but those are offsets, like based on the number is.
Let J go from 0 to D over 2. Here it is. D over 2.
Yeah, I'm trying to get the mean of it. Right?
No, I mean, let J go to from 0 to D over 2. Then do you agree that 2J plus 1 at first is 1, then 2J is 2, then 2J plus 1 is 3. So 2J plus 1 means the odd elements, 2J is the even elements.
Yeah.
Okay, I mean that. So I use these two formulas for odd and even elements to fill out the vector P. Yes, and it depends also on the position I it has. So, and I'm visualizing it here in this figure. So the first row is P1. Yes, P1 for the position of X1. The second row is P2, the position of X2, position vector of the X2.
The second word in the sentence?
Yes. P3 until, for example, here we have P10. As you see, the rows are different.
Yeah.
The vector, it means that the positions has been encapsulated. The position of the first word is different from the position of the second word, from the third one. You see that? And also, you should note that the difference of the position vectors usually lies in the initial dimensions of P. P is the position vector encapsulating.
But here it says P equals 100.
Oh.
Where did I say?
Oh.
Where did I say P equals?
And figure in the comment figure 10. I think that's the.
And also in
the main paper.
in the equation, there is a number P in the cosine sine function.
Which one are you talking about?
Go to the main paper.
Oh, it's the normalization
Pages.
exponent. And it's fine, but it's not bold P.
I still didn't get what you mean.
2J over P.
This is the main paper.
Yeah.
In the caption, caption of
Go
the
down
same
one page.
image.
Go down one page.
Yeah.
Figure 10, caption P equals 100.
Here I mean that
But that's the normal.
No.
P in your.
no, these are two different
They're
P's.
different P's.
That's cap. This is not bold P. This is bold P. When I say bold P, it means the position vector. A small p is a dimensionality of, I think, query dimensionality of, what was it?
So the size of the position vector itself.
Let me see. It's a dimensionality of, see, it's a dimensionality of query and key.
Yeah.
Do you see that? So the dimensional equation 13 and 14. So it's a dimensionality of the small p, but that's capital P. You shouldn't confuse it.
Go back to the figure 10. These are all different words, right? It's like the actual words in the sentence. So what we're seeing is this difference coming from combination of the words encoding and its positioning, or
So that what I'm saying, that we made a vector which encapsulates the position of the xi in the sequence x. So
only the position, not anything about its encoding.
no, only its position. Okay, and as you see, the difference lies more in the initial dimensions of p, and now I add x with p, xi plus pi. Now the addition has the information of both embedding of the word and the position. Okay, that's what we have here in the encoder. See, we have addition here, addition of position and the input embedding. Okay, now we go inside here. Now we have multi-head attention here, as you see. What is multi-head attention? So we use multi-head attention with self-attention. What does it do? This module applies attention mechanism for H times. That's why it's called multi-head. H stands for head. Okay, it's for H time. And what is it? It's intuition. What is its intuition? I tell you. So I want to see how each word attends to every other word. The first head, the second head. I want to see how every pair of words attend to every other pairs of words. Head 3. I want to see how every pairs of words attends to other pairs of words. So it's kind of like a perimeter hierarchical. So every word to other word, every other word, every pairs of words to every other pairs of words, every pairs of words to every other pairs of words. And as you see, it can become very strong because it's calculating the attention of all of the pairs. Okay, so that's why we have multi-head attention, and this measures the attention or similarity between hierarchical pairs of words. And why is it self-attention? Because query, retrieval, and key, these three arrows are from the same sequence. I want to see in the same sequence how every word is attending to every other word, how every pairs of words attends to every other pairs of words. So that's okay. And for multi-head attention, so we have H of them. Do you remember this formula? We just showed that in the matrix form. Q, V, K. So using the learnable parameters WQ, WV, WK, we transform X to Q, query value and key. And then we calculate the scaled dot product similarity, which we talked about using the softmax and all of those things. Okay, and then we have H of them, H similarities or H attentions. Okay, Z1 to ZH. Then it concatenates them. It becomes a very big vector. And then using WO, some other learnable layer, it gets Z total. Okay, it gets Z total. So as I said, we concatenate Z1 to ZH. Why do we have? Because we have H heads. So we have H attentions, right? Z1 to ZH. We concatenate them. Then WO, some learnable parameter again. When I say learnable parameter, these are weights of neural network. WO transpose, that concatenation will give us the Z total attention value. Okay. Now what happens? Then we are here. We are here right now. Okay. Then we have, do you see this? This is add and norm. It is written add and norm. And what does it say? It first adds input of multi-head attention to the output of multi-head attention. Input of multi-head attention X, which has the positional encoding in it too, to the output of multi-head attention. What does it remind you of? That's exactly used in ResNet. This is residual adding done in ResNet too. In ResNet, we add, so we have some block, we add the output of that block with the input of that block in ResNet. This is the idea behind ResNet. So they have adopted that idea here too. Okay, so we have ZT prime. Then they do normalization. Norm stands for normalization. And they just, what do? They do a standardization. This is also related or can be seen as batch normalization. Batch normalization is one of the regularization methods in neural networks. Okay, so batch normalization, what does it do? It makes the standard deviation 1 and the mean 0. Okay, it makes it normal, standard normal distribution. Okay.
The residual links there are from the previous head, right?
So the input of multi-head attention is added to the output of multi-head attention.
Whereas encodings, pairs, words to pairs, pairs to pairs.
So yeah, we had H of them, we concatenated them. We concatenate them.
But with those
It
two things, 1 to 1, 1 to 2, 2 to 2. Right?
Yeah.
Is that the 3 parts within these multi-heads?
No, it's not just 3. Can go to 4 pairs of pairs.
Okay,
Yeah.
opposite.
Yeah, H of them.
But that's in each of the, does that hierarchy happen within each multi-head attention? No here? Or is it the fact that there's multiple?
You mean addition? Do you mean addition?
I guess this concat.
So each of these, Z1 calculates the attention of every word to other words. Z2 calculates the attention of every 2 words, every pairs of words to every other pairs of words, and so on. We have H of them. We concatenate them.
Yeah, kind of this entire picture here.
Yeah.
That's that block. So maximal hit attention, that block.
So we have, yeah, we have H values, we have H keys, we have H queries. Therefore, we have H attentions. We concatenate them. Then we have, by a linear projection, we have ZT. Yeah. So this is multi-head attention, which multi-head attention, you see it here. This is multi-head attention, right? Then output of multi-head attention is added to the input of multi-head attention, and then we do a standardization, also called Z-score normalization, and these things. Okay, so afterwards we have what? Feed-forward layer. Feed-forward. Why do they do that? Just to add parameters to be able to learn. Okay, and then again adding, as it done in ResNet, and again batch normalization, layer normalization. So this gives us the output of encoder. Now encoder is done. So we have the context vector in the transformer. Okay, now let's, by the way, before it's done, we should say that it's stacked n times. Why do they do that? N times, usually n is equal to 6. So they stack the whole thing n times. Why? Because to have more parameters to be able to learn the whole internet data. Okay.
Like make it higher or out.
So you put this and then this again, again, and again. Yes. Yes. So then if by this, they are adding more parameters. They want to, otherwise they will overfit. Okay. The more you need to have a lot of parameters, but if you, by adding this parameter, you need to have a lot of data, big data to train. Otherwise, you will overfit again. So they are adding stacking, but they know that they have the whole Wikipedia and the whole internet data text. Okay. Now, decoder of transformer. Then here it is. This is a figure of the decoder of transformer. What do we have? Again, we have multi-head attention as seen here. Multi-head attention. So what does it do? It's similar. So we have positional encoding similar to before. So we have output of the decoder, but shifted to the right. Why? Because we usually generate one word at a time. When we generate the next word, then we shift the whole thing to one to the right. So output of the decoder shifted to the right. We have its output embeddings by word2vec and these things. Add the positional encoding by the position of the word in the output sequence. We have them, then we have multi-head, like masked multi-head attention. The only difference is masked. So the previous one wasn't masked. What is this difference? Why do we have masked? By masked, we mean here, masked attention. We mean that we only care about attention of every word and every pairs of words to the previous word, not to the forthcoming. In input, we already have the data. So we can calculate the attention of every word to the previous and words afterwards. However, in the generated data, we are still generating the words. We don't have yet the next words. Therefore, we need to mask it to only attend to the previous words. And how do we do it mathematically? We can add some matrix M, whose ijth element is this. If j is less than or equal to I, give it 0. And it doesn't have any effect in softmax. Why? Because in softmax, we have e to the something, right? Then e to the something, e to the 0 becomes 1. So e to the this plus is. E to the a plus b becomes e to the a, e to the b. If b is 0, e to the 0 becomes 1. The multiplication by 1 is nothing. Then, but however, if b becomes minus infinity, what happens? If we put minus infinity, e to the minus infinity becomes 0. Then multiplied by 0, it means that for the next words, we don't care. We make the attention 0. Okay, this is masked. By the way, here also the fact that we don't have the next words and we are masking, it can be seen as the idea of sparsity. We are making it a sparse. We saw the same idea in dropout technique, but it was in the stochastic manner. Here it is deterministic. Sparsity works well usually because of two reasons, which is not time for explanation. One of them is Bethan sparsity in machine learning. The other one is Occam's razor in logic and philosophy. Okay. Okay. So we have masked multi-head attention. Again, we have add and norm, ResNet idea and normalization. Then now interesting thing here is multi-head attention with cross attention, which is this block. Multi-head attention with, as you see, query and keys come from the output of encoder. Values come from the decoder here, right? From the output of masked multi-head attention after ResNet and idea and normalization. So we have cross attention, and what does it mean? It means that how the generated output is related to the input words, because value is from the multi-head attention, masked multi-head attention in decoder. How is every generated word related to the words in the input? Okay, so cross attention we have, and again we have a feed-forward neural network layer for the sake of parameters to be learned. Again, addition and normalization. See, ideas are repeated. Then this thing, which we talked about, is a stacked n times, just for having more parameters, learnable parameters. N again is 6, usually. And then we have a linear layer again, for the sake of learning parameter. And we have softmax. Why do we have softmax? Because we want to make it like probability. Why? The number of neurons in the output of the decoder is the size of dictionary, the number of words in the dictionary. Okay, and the softmax gives us a probability, they sum to 1. It means that the word or the neuron with a higher probability, either it might be very low because we have, for example, 200,000 words, something like that. They might be small, but it's still one of them is larger. That larger is the next generated word because it's more probable to be generated. Okay, so the large. And let's talk about complexity of attention. So attention is all we need, first off. And attention, so we don't have any notion of recurrence. We don't have. So even if you see, you are outputting the output with one shift to it, but it's still it's not recurrence. You're just outputting, generating again as to the input. But why is it recurrence? Recurrence, if you take a look at that in the RNN, something like this. So you have input, you have outputs, for example. These are hidden states, for example. Again, and you have these things. You have something like this. You don't have such notion here in this network anymore. So you don't have any recurrence. And that's why they called it, let's have attention. What we talked about is all we need for learning a sequence. And it was a breakthrough in NLP, state-of-the-art NLP. Nowadays are based on that. Also complexity comparison. Okay. In attention, we have n words in the sequence. We learn a p-dimensional embedding for every word, right? And hence the complexity of operations per layer is O(n squared p). Why? We have n words in self-attention. We are attending every word to every other words, therefore n squared. And p-dimensional embedding for every word, n squared p, as you see it here. However, in RNN, it can be proved that it's O(n p squared). Also, although you might say that O(n p squared) is better than O(n squared p), but the operations in attention can be done in parallel. So we can do it in GPU cores. Okay, so it's good. Also, attention processes all the n words simultaneously, right? However, recurrence, RNN and LSTM, they do it sequentially because of recurrence. Therefore, their sequential operations is O(n). However, in attention is O(1) only. Okay. Also, the maximum path length between the words. For attention, it's only 1. Why? Because you are calculating the attention of every word to every other word. However, in recurrence, you need to pass through all of the words in between. So it's O(n). In these two, attention is better. Even in this one, which is not better, we can do it in parallel. So attention is overall is better. Now let's talk about BERT. BERT is short for, so we are going to talk about BERT and GPT. BERT is short for bidirectional encoder representations from transformers. Okay, it's one of the state-of-the-art. Both BERT and GPT are state-of-the-art in NLP. What is it? It's a stack of encoders of transformer. So do you remember? Transformer is an autoencoder having encoder and decoder. If you only consider the encoder and stack them up, it becomes BERT. If you only consider the decoder and stack them up, it becomes GPT. Okay. So there is difference. We'll talk. So what?
Say that again.
So I'm saying that only consider the encoder of the transformer, several stack of them, it becomes BERT. Only consider the decoder of transformer only, and stack them up, it becomes GPT. Okay, but we'll see the difference. See, so BERT has been used in question answering, NLP, natural language understanding, sentiment analysis. These are tasks in NLP, language inference. Also, BERT is a masked language modeling. What does it do? It masks 15% of the word, and so it considers them as missing word, and every transformer in the stack should predict the missing word. So here, for example, I have the sentence Mona Lisa is a portrait by Leonardo da Vinci. Once I mask Mona Lisa, it should predict Mona Lisa based on the other words. Once I mask portrait, once I mask Leonardo da Vinci, or something like that. And then, as you see, it's an unsupervised. Why? We can mask anything. You give me some text, some corpus, I just mask some words. Therefore, it can be trained on the whole internet data text. That's why it has huge text data, because it's unlabeled. You don't care. It generates its labels itself. Okay, so it masks them. BERT is bidirectional, hence the name BERT, bidirectional. Why? Because when you mask a word, you have the words afterwards and beforehand, both. So it's bidirectional. Based on the words beforehand and forthcoming, what is the missing word? It's bidirectional. Okay. It jointly conditions on both previous and right context of every word. And it is a context-aware embeddings, as we talked about. Context-aware embedding in contrast to word-to-vec and GLOB. Different BERT embeddings in various sentences, such as money is in the bank or some plants grow in the bank of rivers. And also, it gives us an embedding for the whole sentence in addition to the embeddings of every word. So it gives us an embedding for every word. It also gives an embedding for the whole sentence. And you can use that embedding for the whole sentence for spam detection and these things, right? You can train a classifier based on that embedding. The BERT model is usually not trained from scratch because it has been trained by the huge amount of data and for a long time. So usually people do transfer learning or add one layer or several layers at the end. They either freeze the weights of BERT and they train the weights of the added layer, or they fine-tune the weights of the BERT. Both approaches are correct. Okay. The parameters of encoder in transformer encoder. We have 6 encoder layers. Do you remember? N was 6. 512 hidden layer units in the fully connected network, and H attention heads. H is 8 attention heads. However, BERT, although it uses encoder of transformer, but it makes change in it. It makes it more complicated, more parameters to be able to learn more. So 24 encoder layers, now N is 24, 124 hidden layer units in the fully connected layer, and 16 attention heads, H is 16. So it makes it more complicated. Usually when we say BERT, it's called large BERT with these, what we talked about. We have some, when we want to implement it in embedded systems, when we did small, we can't embed the whole large BERT in the embedded systems, such as in phones, smartphones. So we need, there are ways to do it: small BERT, tiny BERT, distilled BERT, Roberta BERT. And what do? They usually do knowledge distillation for network compression. What do? They have a teacher, they have a student. Okay, this is what knowledge distillation does. The teacher is a large BERT, the student is a small BERT, with a small number of parameters. Then the student tries to mimic the teacher. Therefore, the behavior of student becomes similar to the behavior of teacher, although it's smaller. Okay, this is how knowledge distillation works. So we are distilling knowledge from teacher to the student. Some BERT models, such as clinical BERT and bio BERT, also have been used in medical texts. Now GPT. Okay, sure. Bye. So GPT, generative pre-trained transformer, or GPT-1. GPT, because we have several types of GPT. GPT-1, generative pre-trained transformers, stands for that. Is another state-of-the-art method for NLP. It was developed by OpenAI. Okay, this is a stack of decoders of transformer, stack of decoders. In other words, it is built using transformer decoder blocks. Okay, in GPT, multi-head attention with cross attention is removed. Why? Do you remember one of the modules in the decoder of the transformer was multi-head attention with cross attention? We we can't do cross attention. There is no encoder anymore. Okay, therefore they have removed that, and there is no encoder in GPT. Okay, hence the decoder blocks, they use only positional encoding, masked multi-head self-attention, and feed-forward layers with adding from ResNet idea and layer normalization and activation function softmax ones. Okay, as GPT uses the masked multi-head self-attention, okay, it considers, so it is using masked multi-head, right? Do you remember in decoder we have masked? And the reason was that we haven't generated the next words yet. Again, it means that GPT also is using mask. It's only conditioning on the previous words. BERT was conditioning on the both previous and forthcoming. That's why it was called bidirectional. GPT is only conditioning on the previous words. That's why GPT is a generative model. BERT is a masked language model, language modeling model, whatever we call it. So it predicts the masked word. This is the task of BERT. GPT, however, generates the next. So you give a paragraph to it, it continues that, generates the next word. And that's what we see in ChatGPT 2. Okay, so as GPT uses the masked multi, not bidirectional, it conditions only on the previous words. And the objective of BERT was to predict a masked word, but here GPT is a language model. When we generate the next word, it's called language model, whose objective is to predict the next word. The predicted new word, when after prediction of the new word, then it is added to the sequence again and fed back to the GPT. Do you remember we shifted to the right? That's why when you are chatting with ChatGPT, it remembers what we have said before. Okay, and it continues with the context that you had chats before. Okay, so in other words, GPT model tasks takes some document and continues the text in that. For example, if you give a paragraph about psychology, it continues the psychology document, something like that. It is unsupervised. Why? Because you can take any paragraph and you continue it. So it can be trained by huge amount of internet data. Okay. When this is the benefit of being unsupervised, you have a lot of data. So the success. Yeah. Yes, exactly. And that's why both BERT and GPT are unsupervised.
Yeah,
And no, they are BERT is encoder, GPT is decoder.
Oh, that's right. Yeah, they don't actually.
Yeah.
How does GPT get away without encoder? That seems odd. How it's still encoding.
Because do you remember the decoder of transformer gets two inputs, one from its own output shifted to the right, once from the encoder.
But in a sense, they're still encoding words and language, like the GPT has an encoding of words, but it's not using the transformer encoder pattern.
Yeah, it uses both encoder and decoder use the embedding vectors of the words by word to vec.
Yeah.
But yeah, and why can GPT get rid of the encoder? Because it has two inputs, one from its own output and one from encoder. It says, I don't want the input from encoder anymore. I only want the output to my own output. Okay, I want to be only self-dependent, something like that. Okay, then GPT-1, GPT-2 came after GPT-1, and GPT-3. Now I think we have GPT-4 too. Yeah, so more number of stacks of transformer. They are adding more and more number of stacks. They're adding more learnable parameters. GPT-2 had 1.5 billion parameters. Can you believe? And GPT-3 has much more internet data. So they're training. Also now they have the data of ChatGPT, so they can train much more. GPT-2 has 8 million web pages have been trained on 8 million web pages. GPT-2 cannot be easily used in embedded systems, GPTs. So they do knowledge distillation to make it to compress the networks, small, medium, huge, X large, and distill GPT-2. We have all of these are provided for embedded systems, and they have been provided in Hugging Face transformer Python package. Hugging Face is a library for NLP in Python. Okay, GPT-2 has been used in many different applications such as dialogue systems, patent claim generation, medical text simplification, question answering, and I think now it is in chat. It is noteworthy that GPT can be seen as few-shot learning, so some papers have discussed that. Also, a comparison of GPT and BERT, you can see it in one of the references. Also, you should note that for the sake of comparison, GPT-2, NVIDIA, Megatron, Microsoft, Turing, NLG, and GPT-3. So GPT-2 has 1.5 billion parameters. The NVIDIA has 8 billion. Microsoft Turing has 17 billion. GPT-3 has 175 billion learnable parameters, a huge jump. Okay, GPT-3 has been trained on internet data with various subjects. That's one thing. On poetry, mathematics, whatever you can think. So hence GPT-3, it can do almost all topics. And some people are saying that it's passing the Turing's writings award. Sorry, Turing's test. And some people are discussing that GPT is kind of memorizing the text. However, in a good way. In a bad way, it's called overfitting. It can't generalize, but in a good way. It's so memorizing in a good way. It can generalize well, because it has been trained on the huge data of internet. Also, it has a huge number of learnable parameters, so it doesn't overfit. And it can also work on fiction and poetry generation. You tell it write a poem in the style of Shakespeare, and it will do it for you. Yes, some acknowledgements. These slides were inspired by the teachings of Professor Ali Ghodsi and Professor Pascal Poupard at this University of Waterloo. Also, this is our tutorial. You can take a look at that. Attention mechanism, transformers, BERT, and GPT tutorial and survey. These are the references. Just for the sake of recording, I'm going through them because people might want to see the references. By the way, while I'm scrolling down, please note that I have a YouTube channel. I'm gonna upload this also on my YouTube channel. Feel free to subscribe to my YouTube channel. I put a lot of lectures there. I'm teaching at the University of Guelph. Also, I'm putting my lectures there. This semester, I'm teaching both statistical machine learning and deep learning. You can take a look at that, and just search my name, Benyamin Ghojogh, in YouTube, and this is the YouTube channel. Feel free to subscribe to that. Okay, thank you. Any question? Was it good? I don't know.
It's amazing.
Yeah, no, really great deep dive. So, does any follow-up questions we asked along the way? Like, we're over time, I have to let you go, but I still got 10 or 15 minutes if I can stay. Does anyone have a question they want to go back to?
For equation 12.
There you go.
The question?
Equation 12. Yeah.
Let me.
You should try to come out like, oh, don't have a big question, or if you do, it's like, oh, there's so big question hanging on something.
Or this.
We should read a paper about that next.
Okay, so let me find it. How could I? Oh, here.
Oh, yeah. I just checked that again. I wasn't sure how it works. Like I thought, the live,
Yeah.
the fact that you're sharing your screen, remarkable.
Yeah.
I didn't think you could work wirelessly, but apparently they upgraded the software with this.
Question 5, you said?
12.
12.
The similarity measurement.
Okay. Equation 12, right.
I've seen that before. Is it proposed to like increase the time efficiency of attention? Because the rest of the 3 is like multiplication, but 12 is like doing the adding operation. And if we mix the similarity measurement with the projection matrix, and we can treat the WQ and WK as the matrix, the projection matrix somehow, and the rest would be just an add operation. And I think it's like faster than multiplication.
In my opinion, there is no difference in pacing because also in 12 we have multiplication. W transpose Q, W transpose K.
But if we think WQ and WK as projection matrix, because we need to do the projection for all the attention thing, then
But you have a pairwise add, like element-wise add and 2 vector multiplications. The other one is,
I think it's just a choice. a choice, and I think there is no preference. However, people usually prefer equation 9 or 10.
Yeah.
They usually use 10, equation 10 for in transformers,
Someone asked about 10, why square root p?
just for the sake of normalization.
Because we're square, right? Because at some point we got, well, Q and K are vectors of similar size and everything, so essentially,
Why second root, you mean? I have no idea why. Yes, second root of p
not on your slide.
is what?
Sorry, you just mean square.
Second root, yeah,
Sure.
square,
Or as people say, square root.
square root.
But because we're multiplying, I mean, Q times K, we're multiplying a variable twice and having all elements, so it's like, because Q T K is like doing Euclidean distance without the square root, so the dividing by square root.
No, Q transpose K is the similarity, the inner product. But I can say one thing. I can say that if you consider Q not to be normalized, let's normalize it. Let's normalize K also. Okay. But they apparently they have normalized it by dimensionality. For example, the dimensionality of Q is P rather than that by norm. They are normalizing by dimensionality. Rather than okay, what is the dimensionality of K? Also P. So they have Q transpose K over P squared, but I don't know why they have put rather than P squared, they have put square root of P. But that's, do you know what, doesn't matter. That's why you can use equation 9 too, because scale is not important. Whatever you do, the learnable parameters, but they adjust themselves.
So we're getting a similarity score, and the highest one will be 1, right? Fact that probability
Yes.
isn't actually that important.
Yeah, that's what I'm saying, that the scale is not important. I think that's just a fancy thing, because the learnable parameters will adjust themselves. For example, if you use equation 10 rather than 9, then if square root of P is not required, the learnable parameter will be multiplied by this will be square root of P times W rather than W, something like that. So they will adjust themselves.
It might be something that would be some scale, like class and things like Z norm, right? You normalize it by the standard deviation. We kind of get makes that the number is in the same kind of scale as the original values. So maybe that helps. But yeah, in terms of getting an output, picking the highest value, then just. But added is interesting. The Q, if you just multiply WQ and WK, you wouldn't necessarily just get W right off, right?
Which one?
You got those two vectors.
Okay. In equation?
Well, what do you have there? This is
Okay.
Is W just?
W's are the learnable parameters.
No, I know. The two vectors W, they represent everything that capital W would represent, but they're not necessarily just be multiplied them. These get W.
So the difference is that capital W is a matrix, so you can see it as a linear layer or something like that. However, WQ and WK are just a vector, so you can see it as a connection of one neuron to all other neurons in the next layer.
It's almost like a separate linear thing.
Yeah,
If
maybe.
you made them into a matrix, you wouldn't necessarily get W right away, but they're encoding the same thing.
Yeah,
right?
maybe.
It's all the same. Cool.
Okay.
Other questions?
Other question? No?
Definitely has some somewhere, but that could be like, what would we focus on? Because this is great. It like leads us up to especially went through more of like what's up before than I actually thought we would. So that's good, like the LSTMs and RNNs and why those didn't work. Because like when I was in grad school, yeah, I guess NLP was that everyone wants to do language and do AI for language was not working. Like in the 2000s, like they had rules and logical systems and it was getting slightly better, but never gotten much better. And they're trying to use RNNs, like all LCM start working a bit. But there was a hopeless thing that like language understanding would never get past a certain point. Like really, like 20 years ago, people were like hopeless. No, let's do like LSTMs are great because they can do this stuff with a classification and even an image understanding and started moving and getting better. But language was like depressing. People were like, no, just don't do it. We've done as much as we could. We understood grammar. This stuff's never going to work. So the fact that this just works now, it's like shocking, you know, because they had to give up on RNNs and LCMs and say,
Yeah,
don't remember previous words
yeah, exactly.
in a way. But still, like, why, what's the essential difference? How does that all work together?
Yeah, exactly.
Like, some of these pieces still seem kind of arbitrary. Definitely your description helps us, I think, for me, anyway, it makes it seem a little less arbitrary that all these pieces have a meaning.
Yeah. And this is a YouTube channel, by the way.
Nice.
You can, yeah, you can take a look at it. As you see, where these are, see, yeah, I have playlists. So I taught optimization techniques with, for example, sorry.
And cooking show.
So here, for example, as you see, the preliminaries, linear programming, linear integer programming, sensitivity analysis, KKT conditions, gradient descent, backpropagation, ADAM, using neural networks and this. Yeah, proximal methods, Newton's method, interior point method, conjugate gradient, quasi-Newton distributed optimization, at ADMM, for example, non-convex, sequential convex, metaheuristic, Riemannian optimization, and these things.
Did you add
Riemannian, yeah. So Riemannian, here it is. Introduction to Riemannian optimization. It was a bonus lecture.
Yeah, the whole thing.
Yeah, and there are other playlists such as statistical machine learning this semester, also deep learning. You can take a look at those, and yeah. But
Okay,
just,
those slides from manifold dimensionality.
yeah, I think we'll cover that in statistical machine learning. Okay.
Good.
Thank you.
Yeah, thanks.
Okay.